Okay, the relativity of time, time dilation. Two concepts. We're going to define the proper time and then state the time dilation equation. We are going to invent a clock today. It is a light source, could be a laser, sends up a pulse of light. So just you flick it on, flick it off. Sends this pulse of light up to a mirror. That light pulse bounces off of the mirror and comes back down to a detector located essentially in the same spot as the light source. And each time, then if you wanted to keep on ticking, then as soon as that detector receives the light pulse, then it tells the light source to send another one, and that could be your ticking clock. The idea is that the light has to travel twice the distance between the detector and the mirror for each tick on the clock. Now, if we ask what happens if you place that clock on a rocket. Here's the clock, and here's an astronaut in the rocket, and this clock is going to measure a certain amount of time between ticks. We're going to call that delta T naught. But then, while that rocket is moving past the Earth, at some speed v, then an observer on the Earth is going to watch this same thing happen. It sees event number one when the source emits the light pulse. That's this. So this observer on the Earth, sees the light pulse emitted, travels to the top, a distance d, bounces off of the mirror, comes down to the bottom. But in the meantime, the rocket has traveled a distance L between for the first leg and another distance L for the second leg. So if you really believe Einstein's second postulate, the speed of light postulate, then you're going to say, well, hold on here. The observer on the Earth, watching this light travel from event 1 back to event 2, event 2 is when the pulse reaches the detector, that light has to travel a farther distance, a distance s, which is related by Pythagorean theorem to this distance L and the distance d. In fact, s is the square root of d squared plus L squared. So that's a distance it travels during the first leg, distance it traveled during the second leg. The light had to travel farther, but the speed of light is independent of the motion of the observer and the source. And so she's going to say that light had to travel farther. If the light travels farther, given the fact that it's still traveling at the speed of light, independent of the motion of that source, it had to take longer. So the observer on the Earth sees the light pulse travel a greater distance between ticks and measures a time passing more slowly. It takes longer for that clock to tick once from the point of view, from the reference frame of that earthbound observer. All right, so let's define the proper time. Same diagram here, but now we're going to define this proper time. The proper time between two events is the time interval measured by an observer who sees the events occur at the same place. Okay, we've got two observers. We've got an earthbound observer. We've got an astronaut. Those are our two observers. The astronaut has his XYZ coordinate system. The earthbound observer has her XYZ coordinate system stuck to wherever she is. And we want to know which is the proper time. The time that she measures, which is longer than the time that the astronaut measures, or the time that the astronaut measures. But the proper time is measured by an observer who sees the events occur in the same place. Well, here's from her point of view, event 1, when the source emits the light pulse, the rocket's over here. And when the light pulse reaches the detector, the rocket's over here. So from her point of view, the first event was for a negative x out here, negative 500 meters or whatever it is. And then the second event is for x that's positive out here, x equals plus 500 meters. Minus 500 meters over here, plus 500 meters. They're not occurring at the same place. Well, what about the astronaut? He's got his coordinate system. The event 1 is right there at his feet, right where that clock is. And event 2 is also right there at his feet. Those two coincide. We told you that the detector and the light source are really close to each other. And so the two events occur at the same place. So here, events 1 and 2 occur at the same place. Hence, the astronaut measures the proper time. Because those two events occur at the same place. Perfect. And so, in fact, we'll use delta T naught generally to denote the proper time. All right, let's actually calculate what the difference between the times is. It's not that hard. And the same diagram here, but now what we're going to do is just put the math to it. So first of all, I'm going to ask in the reference frame of the astronaut, the light starts here. The time delta T naught is the time between ticks. So it's the time between leaving the light being emitted by the laser pointer, hitting the mirror, and coming back down. But let me just focus on half of that time, delta T naught, the time it takes for the light to go from here to here. So that's delta T naught over 2. The distance traveled is d, and the distance is the speed times the time. But the speed is the speed of light. So that's distance is speed times the time, which is half of that time for the whole tick of the clock. Well, what about for the observer? The distance traveled for this first leg is s. So the distance is the speed. We have to use the speed of light, right, because of the second postulate, times the time, delta T over 2, but she's measuring a different time, remember? So instead of delta T naught, it's delta T, a longer time. And then finally, from the point of view, from the reference frame of this earthbound observer, the rocket is moving. And it travels during this time, delta T over 2, it travels a distance L. And the rocket is traveling at a speed v. And so the distance, L, that it travels during this time, delta T over 2, equals the speed of the rocket times that time. So that's the essential physics right there. The rest is just algebra. But if you can write these kinds of equations down for the problems that you'll be doing, you'll understand. And we'll give you a couple more examples. All right, then let's do some geometry. We wrote this down before from the Pythagorean theorem. This distance s squared is the L squared plus D squared, or D squared plus L squared. If we then substitute this equation for s, so that's going to go in here. This equation for D, and this equation for L, then just plug the numbers in. We get c squared delta t squared over 4. We get what you see right here. Just plugging those three equations in. The 4's all cancel. And we can divide by c squared, which gives us delta t squared is delta t naught squared plus v squared over c squared delta t squared. And what we're interested in doing is solving for delta t as a function of delta t naught. Well, here's a delta t squared, and here's a delta t. So if we subtract this term here from both sides of the equation, we'll get delta t squared times 1 minus v squared over c squared, and that'll equal delta t naught squared. Take the square root of both sides, we'll get a delta t times the square root of 1 minus v squared over c squared equals delta t naught, and then divide both sides by 1 minus the square root of v squared over c squared, I mean the square root of 1 minus v squared over c squared, and we get this relationship here. Which one's bigger, delta t naught or delta t? Well, we know that delta t naught is the shortest amount of time, and we're going to divide by 1 minus v squared over c squared. V here, remember, is the rocket velocity, rocket speed. C is the speed of light. The rocket speed is going to be less than the speed of light. So this number here will be less than 1. I'll have 1 minus something that's less than 1, which will be less than 1. And the square root of something that's less than 1 will still be less than 1. And 1 over a number that's less than 1 is greater than 1. So that says that delta t will always be greater than delta t naught. And here's the concept that captures all of this. The dilated time is always longer than the proper time. The shortest time that you'll ever get is the proper time. So here's the equation that we just derived. Here's the definition of everything. Delta t naught is the proper time. And what's the proper time? It's the time measured when, let me just remind ourselves, the proper time between two events is the time intervals measured by an observer who sees the events occur in the same place. That astronaut measures the proper time in this particular example. So this is the time measured by somebody who sees the events occur in the same place. The dilated time is the time seen by anybody else observing that's not in that, that particular reference frame. The relative speed is v. That's everything's relative, right? And then c is the speed of light. So notice, just like we did with the index of refraction, when we had a ratio of two speeds, here we have v squared over c squared. V squared is measured in meters squared per second squared. C squared is measured in meters squared per second squared. Units cancel, and we'll get a time on the left-hand side and on the right-hand side. The interesting thing about the proper time is that if I watch you in your spacecraft moving away from the Earth in any direction, all this works in any direction. You could be approaching me, you could be going away, you could be going sideways, and I watch your clock. Well, I watch my clock while you're moving in your spacecraft. I'm watching my clock, and my clock's running just fine. It's ticking off the seconds, 1,000, 2,000, 3,000, etc. But I use my telescope and look at your clock, and I say, your clock is running slow. And because it takes longer, from my perspective, watching your clock, it takes longer for your clock to tick. And this not only works for this kind of idealized clock here, but any clock. You can use a watch. If I used a telescope and watched you as you're going away in your rocket, there was a nice mirror or whatever, and I could, or a window to see. But then you can say, well, hang on, Dr. Edwards, you're wrong. My clock, the astronaut on the spacecraft, is running just fine. I can look at it at 1,000, 2,000, 3,000, no problem. Dr. Edwards, your clock is running slow. And so who's right? And why does the astronaut say that? Because from the astronaut's point of view, he's at rest with respect to his clock. Everything's doing fine. But he's looking at me and saying, hey, you're moving, therefore your clock's running slow. Who's right? Well, you're both right. Anytime I look at you, your clock's going to be running slow if you're moving relative to me. If you look at me, then my clock will be running slow from your perspective. All right. So an example, the spacecraft speed is 0.92 c. So v is 0.92 c. That's 0.92 times the speed of light, which is 3 times 10 to the 8th meters per second. So you can work that out into meters per second if you want. The astronaut measures a time of 1 second on his clock. So he says on his clock there's a time of 1 second. What time is measured by the observer between these two events? Well, we know that delta t naught between these two events is the proper time is measured by the astronaut because the two events occur in the same place. And then we just have to divide through by 1 minus v squared over c squared. We know that delta t naught is 1 second, v is 0.92 c, but we've got to divide by c. Those c's cancel. And we get 1 minus 0.92 quantity squared. And then just plug the numbers in, you get 2.6 seconds. Sure enough, the observer on the Earth says, hey astronaut, your clock's running slow. It's 2.6 seconds between ticks on your clock. Another example. Alpha Centauri is a nearby star, is 4.3 light years away. A rocket leaves Earth, bound for this star, and travels at 0.95 c. So that's v. Relative to the Earth, how long does this journey take, A, for the Earthbound observer, and B, for the astronaut? So let's define the events here. Here's Earth. And here's the rocket. Okay? And event 1 is that the rocket leaves for the star, leaves Earth, bound for the star. Okay? So this is event 1. Event 2 is when the rocket arrives at the star. Here's the star. Here's the rocket arriving. That's event 2. All right? So now, we're interested in knowing who is measuring the proper time. Well, the astronaut has a reference frame. Here's his x and y axes. Let's call them x prime and y prime. They're right here. They're stuck to the seat of his seat in the rocket. So that astronaut is going to see event 1 and event 2 occur at the same place. Well, they don't occur in the same place. You say, well, I say, yes, they do. You're the astronaut. You're sitting in your rocket, and you're sitting on the Earth. Your coordinate system is right here in front of you. You leave the Earth. You launch. You blast off. Where did the blast off happen? It happened right there, where you are. Then you go to the star. You arrive at the star. Where did the event occur? Well, it happened right there, because your rocket landed on that star. So the two events occur in the same place. And the easiest part to do, so in other words, the proper time is measured by the astronaut in this case. The easiest part to do is to find how long the journey takes for the Earth-bound observer. Okay, so let's look for the observer. And let's ask how fast for the Earth-bound observer. So this coordinate system, this reference frame here, was for the astronaut. Okay? But now we're interested in the coordinate system for the Earth-bound observer. So this is you. Here's your Earth-bound observer. He's staying here. He's going to be there the whole time. From his point of view, that rocket is leaving at 0.95 c, going at a speed of 0.95 c. From his point of view, the distance between the Earth and this star is 4.3 light years. That's the perspective that we're usually in. Yeah, we say it's 4.3 light years. So it's easy. The distance between the two events, which is the distance between the Earth and the star, is the speed of the rocket, which we have, times the time required. And that time is not going to be the proper time. The proper time is going to be observed by the astronaut. So we can solve this equation for delta t by dividing both sides by v. So delta t will be d divided by v. So that's this equation here. We plug in 4.3 light years divided by 0.95 c. That's this velocity of the rocket. Now I've put in light years here in an interesting way. But that interesting way makes it awfully simple to do these problems. We talked about light years before, one of the previous chapters. 1 light year is the distance that it takes, the distance that light travels in 1 year. Well, so we can get that distance by multiplying the speed of light times the time, and a speed times a time will give us a distance for a light year. But this c is 3 times 10 to the 8 meters per second, but we're just going to leave it in as a variable. Why? Because it cancels out with that 0.95 c in the bottom. And all we have to do is divide 4.3 divided by 0.95, and we'll get the answer in years. So from the point of view of the earthbound observer, the journey takes 4.5 years. And you say, well, that makes sense because it's 4.3 light years away, the star is, but he's not traveling quite at the speed of light. He's only traveling at 95% of the speed of light, so it's going to take him a little longer. That makes sense. Well, what about how long the journey takes for the astronaut? Well, the astronaut measures the proper time, and we have an equation that relates the proper time to the actual time. And the way that it was written in the concept and the way that we derived it is delta t equals delta t naught over the square root of 1 minus v squared over c squared. But I want the proper time right now. So I'm going to multiply both sides by this ugly square root. And delta t naught will be delta t times 1 minus v squared over c squared. So that's this equation here. But I have everything I need now. I already calculated the dilated time. Delta t is 4.5 years. We know v is 0.95 c. Both observers agree on that the rocket is traveling at 0.95 c. The c's cancel again, and we work out that the astronaut, that from the perspective of the astronaut, it takes 1.4 years to travel to that star. You say, well, so science fiction movies that I've watched about this are actually true, and I say, yeah, they sure are. On that rocket ship, you're going to age slower than they are at home. And there's also a twin paradox where if you and your twin are born at the same time, obviously, you're twins, one of you heads out into space and comes back, then he's going to be younger than you are. You're going to be older than he is if you stayed here on the Earth. There's two effects that go on with that, both the effect of special relativity and also the effect of general relativity. We'll talk a little bit about that as well. But the bottom line is that the astronaut only takes 1.4 years to make it that distance to that nearby star.